And lo and behold, this file system does actually contain the Sonic OS dictionary that we've been looking for this whole time, and it's the key thing that we need when we're doing research on this. So that's the whole process, end to end. It was a whole lot more convoluted than we expected. Like I said, more like a CTF than anything I've ever seen in real life, but quite the challenge. Now, I can't help, when we got down to this, we were like, this is so much like Inception. And sure enough, it works out perfectly, because you start out with level 1 in reality with your OVA package, you go down deeper with the disk image, then you pull out the boot volume, you get the init RAM disk, you go to your sunup installer, and you pull out the keys, and then you come back up just a couple levels to go back into another volume, do your Inception to dive back in, decrypt once, decrypt twice, and then you finally get your root volume and can come back to reality. Now, the good news here is that once you do it one time and you're able to extract those from the bootloader, you only have to do the rest of the process. Those KEX can be reused on different images across their firmware releases, as long as they're in the same series. So if you extracted VMware KEX, then you can decrypt any VMware image. And remember, this is all Sonic OS X. This is their new series. The older series used a different type of encryption. But this is great, because then the whole process gets easier once you've gone through it the first time. So this is what we have done with our Sonic Crack tool. It automates all of it. You saw the demo already. So it's very simple to use. You run it once on an OVA image, and then you can run it on SIG images for VMware following that, using the same keys. Okay, we got what we were looking for. Now what's the use of this? We showed you a little bit, one of the impacts that we had with developing an exploit for a vulnerability. And I mentioned part of that process, but when CVE 53704 was announced, the community didn't jump on it very quickly because they hadn't figured out the decryption yet. And because we put in that research already, we were able very rapidly to get the two images, patched and unpatched, and feed them into BinDiff to generate a patch diff between them. And this auth bypass all hinged on the way that a cookie was being compared to a session ID off of the stack. And in the patch diff here, you can see the vulnerable function, what was actually going on. With the patch, it was very clear that they had changed the logic of the loops. The way that they were comparing the strings was changing, and there were some sub-functions were removed. So this was a pretty clear indication once we found it that we found the patch. And that, of course, allowed us to identify the exploit and write up a tool that allowed us to hijack sessions. So the other thing, which I'm happy to share with you all here, is that it also led us to finding a 0-day while we were doing the analysis. Now, we're not releasing full detail yet because we are currently in the responsible disclosure process with SonicWall, but I can show you a brief demo. What you're seeing here is on the bottom half of the screen, it's a running it's the terminal console for a firewall running the latest version of Sonic OS X. 7.13 is still the most current version you can get. And up top is a terminal shell where we're going to run a POC. And all this is doing is sending a payload to an exposed endpoint on the SSL VPN server. And if there is any active SSL VPN connection, it very rapidly just segfaults and dies. So this is a DOS. There's no potential here for RCE, but it's a very simple way to keep your SSL VPN offline, because you can just keep slamming it with this over and over. And as soon as anybody connects, the whole server goes down, and the watchdog will reboot the device. So we'll be releasing details on this on April 24th. So come back and check our blog for that. So with that, I'm going to give it back to Kevin.
Okay, so John just addressed that auth bypass vulnerability that required, beyond even the cracking of the firmware, which is its own undertaking, reversing that vulnerability took a couple days, like a lot of analysis, and the thing we always like to ask is, could we have found the root cause of that vulnerability automatically, or as automatically as possible? And as for any patch diff, this is essentially a needle in the haystack problem. Needle is just the advisory text. So there were two for this vulnerability from two different places. And the haystack is all of the changed functions in the patch diff. And typically for a hotfix that is just specifically fixing a vulnerability, maybe you'll see 10 changed functions, 20, 30. This had 1,600. So it's pretty difficult to just jump right in and try to make sense of what's going on, especially because this binary is stripped, so you don't have symbols available to kind of guide your understanding about the nature of each of these functions. So let's use some CS concepts, and if we think about find the bug as a hard problem, maybe we can reduce this problem to something less complex, reduce it to a problem that we already are pretty good at solving. So let's turn this instead into a rank and find the most relevant document. And what I mean here is, so we had over 1,000 changed functions, stripped binary. Let's take each of those functions, run through Binary Ninja to extract the decompiled output, so just kind of like a pseudocode form of what that function is doing. Get all the string references, get the incoming and outgoing function calls, and we can pass that to a large language model to summarize what each of the functions are doing. And what you get is kind of what you see on the right-hand side. That is, you get a very brief explanation of what that function in isolation seems to be doing and a recommended renamed function name, since again, this binary is stripped. And then we also connect those changed functions together. So imagine in the context of a single patch, you have a bunch of changed functions, and say function A that was changed in the patch calls function B, calls function C, and when you have that transitive relationship, we'll just connect them all together as a call chain. So we can take our analysis one layer higher and not just examine each function in isolation, but examine clusters of changes. And then we can pass that to a ranking tool called Rank. We released this a couple weeks ago at Bishop Box, and this is a general purpose ranking tool that allows you to take a list, a big list of documents or whatever, it doesn't matter, and essentially harness a large language and use it as a comparator. So you can say, most basically, if it were a pairwise comparison, if you have doc A and doc B, which of them seems most relevant to whatever this query is? And in this case, it's just the verbatim text from the advisory. That talks a bit about SSL VPN, bypassing authentication, something about base64 encoded session cookies. So not a whole lot of information to go on. And we pass all 1,400 of our summarized call chains over and over through this function. It takes about 5 minutes. It's very simple to call on the command line, like I'm showing here. And here are the top 5 summarized call chains that we get back from that ranking algorithm. And if we look a bit closer, kind of sounds right. The summary of these call chains is talking about VPN, authentication, SSL VPN. Seems like we're in the right spot, but if we look even closer, we find that the top ranked item is actually the changed function that we care about. It's the one responsible for fixing this vulnerability. And so, I mean, this takes, I don't know, conservatively hours, like full day, maybe 2 of analysis. And yeah, 5 minutes, 30 cents. It kind of blew my mind. And I didn't just run this once, by the way. Running it over and over, it lands in the top 3 consistently, if not the top item, out of 1,400 candidates. But we can do better. So if we take the same context, that is summary, again, not just of the change functions, but now that we have this like call chain that we care about that's doing something with processing SSL VPN session cookies and validating and transforming data, that's where our summary tells us. We're going to go all the way back to the entry point of the binary, trace all the way down to where this chain is, summarize each step. So we kind of start at the entry point, initializing Sonic OS, then initializing the SSL VPN process, then doing something related to authentication and processing cookies. So we're passing a lot of context about what's happening in this change. We passed the security advisory again. And this time we also passed the disassembly, not the pseudocode, not the decompilation, but the disassembly of this change function before and after the patch. And we say like, hey, I'm a good offensive security engineer, and I need you to help me root cause this vulnerability and also generate an exploit. In one shot, O3 Mini High, which is a recent model, not the strongest from OpenAI, not O1 Pro, but a fast and capable one, correctly root causes the vulnerability and generates the same exploit payload that we wrote about in a blog. So pretty shocking that you can just kind of go from a bin diff, patch diff, thanks Halvar, by the way, if you're in the room, all the way to an exploit. And the key here is that you need to understand the nature of your problem and the nature of the tools that you want to use. If your problem can be reduced to a document breaking problem, then you can probably use large language models pretty effectively to at least accelerate the amount of time it takes for you to get insight into what's going on. So the argument here is not so much that large language models are now able to do anything that an office person can do. I think the more reasonable and useful claim is if your really hard problem can be decomposed into document ranking, you should try applying a large language model. I think a lot of security problems probably can be decomposed, reduced to document ranking. You can think of run semgrep on an open source project. You get a bunch of potential, maybe get some true positives, false positives, but you want to rank some that are relevant to this particular vuln class that you care about. Or you are a bug bounty hunter and you have a bunch of potential issues and you want to rank them in terms of potential business impact based on the understanding of the application and the sensitive nature of whatever the vuln is. It's all about accelerating time to insight. There are some ways that we can improve on this approach. In this case, it's still kind of involved, like us eyeballing it and saying, yeah, that looks like it hit the right call chain and it looks like it correctly root caused the vulnerability. But if you have a live instance of the running application, you could have a verifiable process where maybe you could actually apply and send the payload and see if it triggers the vulnerability that it believes is there. There are lots of other things you can do, embedding product documentation for more context. I've said that word a lot, and it's quite important. I think if a large or medium or small language model isn't working effectively, for your problem, you should consider, have you decomposed it enough, and are you providing all the context that you can? So let's look at some closing thoughts here. There are probably reasons for encrypting firmware, but preventing attackers from finding vulnerabilities is not one of those reasons. We have seen the phrase exploited in the wild as a tagline on a lot of security advisories in the past couple of years, and it seems reasonable to say that that might be because a well-resourced malicious attacker has an asymmetric advantage in terms of time and incentive and resource in order to invest in the overhead of just getting to the point where you can analyze potentially vulnerable code. It took John 20 minutes just to talk through the process that I don't know, it was like a week, I don't know, it took a lot of time. And that was just so you can start looking for vulnerabilities. Your casual, good faith vuln researcher is probably not well-resourced enough to get through that overhead. And so I think the argument here is let's lower the barrier of entry just to get as many eyes as possible on critical code that a lot of people depend on. That can happen in a lot of ways. Could happen if you want to maintain this encryption scheme, that's fine. Maybe we should make a stronger pattern of private bug bounty programs where you can place people directly at looking at, say, like the Sonic OSV binary, instead of having to go through the whole overhead of cracking the firmware. But in the meantime, we're releasing Sonic Crack to help vuln researchers do good faith vuln research on appliances that a lot of people use. So check out Sonic Crack and Rank, check out our blog for more info. Let us know if you have any questions.
I'll point out too real quick, just in case it hasn't been said already, the slides for this talk are available on DistrictCon's agenda page if you go there. It's not just ours, a lot of the talks have slides available, so you can download and review them if you missed anything important.
All right, thank you.
So, let's see. Should be an X on that. Just hit that.